Paulo. Sì. Oh, diciamo. Beleza, vamos começar. Isso é o terceiro encontro. Bom, todo mundo já se conhece. Você não, acho, não diga outras vezes. Eu fiquei falando entre você faz. Eu estou fazendo termos de graduação lá no IE e isso. E assisto mal você 2 semanas atrás da matéria. Melhor aula do mundo. Melhor aula. E até hoje, porque agora vamos assistir a um seminário ainda melhor sobre o memory effect das ondas gravitacionais, imagina. Isso, vai, Nickolas.
Legal. Eu falo português ou inglês?
Inglês seria melhor.
Inglês. Okay, let's keep doing it. Okay, I want to talk about the memory effect, and I changed the title in the last minute from "Don't Forget About Memory" to "The Memory Effect and What It Means for Humankind," which is a joke made by Spivak in one of his differential geometry books. It has a chapter called "The Galvanic Theorem and What It Means for Mankind." And here this schedule I plan on following. I'm going to discuss what is the memory effect in gravitational waves. Then I'm going to talk why I'm interested in it, which involves some things about quantum theory and more formal aspects of gravity. And finally, I'm going to make very brief comments about detecting the memory effect. I'm still not working with the memory effect, so this is sort of a journal flow, but I plan on working with it later in my PhD. So this is sort of an excuse for me to study these things deeper and share it with you. Okay, so the first thing I want to talk about is not forget about memory in gravitational waves. And so I'm going to discuss what exactly is memory. And the memory effect was originally discovered by Zildovich and Bonarev in the 70s. And the basic idea is that if you have two inertial detectors a very large distance from your gravitational wave source, and the gravitational wave passes through these two detectors, you're going to have a permanent shift in the separation. So they're going to get permanently more distance or less distance, depending on the details of the gravitational wave. The basic idea is only this. I did struggle for quite a while to understand, wait, it's that all of it? And yeah, the fact is pretty much this. And how exactly do you compute these things? So how do you calculate how much deviation you actually have? The basic equation is the geodesic deviation equation. So this equation is general relativity. R is the Riemann tensor, D is the initial separation between the two detectors, and delta x is the separation as a function of time for the detectors. So you're going to have this formula, the standard formula in general relativity. You find it in any GR textbook. And to actually compute this fact, you need to find an expression for the Riemann tensor, and making a large R expansion. It's a standard calculation of gravitational waves that the Riemann tensor is going to be given by a derivative of the quadrupole moments of the source. So the quadrupole moment here, as just a reminder, is this integral of the energy density where these factors are positioning it. And so this measures a bit about the shape of the source of gravitational waves. And the curvature is due to how this distribution of matter changes. There are other contributions to this Riemann tensor expression, but I'm only considering the large R terms, so dropping 1/r squared and things like that. So using this expression, we get this expression for the deviation as a function of time in terms of the quadrupole. Now, one model often considered to study the memory effect on physical situation often considered was proposed originally by Roginski and Thorne in the 80s. And the idea is that you have a lot of massive objects, so stars, black holes, or whatever you want, and you're scattering them. So they come in inertially from minus infinity, they interact somehow, so the scattering happens, and eventually go off to infinity, also inertially. So this could be very different stars merging together, interact, and then flying off, or black holes, and so on. if you have balanced states here, so for example, in a black hole merger in which you have two black holes orbiting each other, they eventually merge, you're going to consider the two black holes initially in a balanced state as being a single body. So you can use this inertial approximation. So in the particular case of black hole merger, you would have just one body entering, which is the combined body of the two black holes that are currently merging, and at the end you only have one body again, which is the final black hole. So this is a physical picture that Brzezinski and Paulo consider, and in this case, the quadrupole moment formula gets quite easy. You only have that integral of the energy density with the positions. So when you derive, you differentiate it twice with respect to time, you're going to have only the sum over the different bodies. Okay, here labels each body, and it's the mass of each body, and v are the velocities, which just appeared due to the derivatives of the positions you had earlier. You don't have any acceleration terms in here because you're assuming that at very early times and at very late times, which are the times we're interested in, the bodies move inertially, so they have zero acceleration. I'm working in an approximation which we consider a background Minkowski space, and considering how this bodies perturbate Minkowski space on top of it. So you have this simple expression for the derivative of the quadrupole, and using this in the earlier equation for the geodesic deviation, you're going to find that the deviation, the experience is going to be proportional to the original displacement, which makes sense. The more displaced they were initially, the more they will be later. You have this contribution from the R term that occurred to the Riemann tensor in that expression. And then you integrate twice. Let me remind you what about the previous formula. You had this, so you just integrate twice, and you're going to find this expression. You just need the total deviation from the very early times to the very late times. So before the gravitational wave passes to after the gravitational wave passes, it's going to be given by this expression. By evaluating this second derivative of the quadrupole moment, we can then get to this final expression, which relates the initial masses and velocities to the final masses and velocities of the bodies that have been scattered. And this formula was originally derived by Brzezinski and Paulo in the 80s. And their formula was actually a little bit different. I'm writing it in a different way here. Their formula was for the gravitational field rather than the actual deviation. But I think that for first contact, it is a bit easier to see the deviation. I find it more illustrative. And an important comment to make here is that if you have the situation with black hole mergers, in this scenario, which I'm using linearized gravity, then the quadrupole moment will not change before and after this derivative of the quadrupole moment will not change before and after the merger. So this formula vanishes, which means that you don't have memory at this linear level in a black hole merger, which makes it difficult to detect it in the experiments we have nowadays, which go mainly black hole and neutron star mergers. So you have this limitation. And this is an analysis done in the linear approximation. So you're using linear gravity to derive these equations. And the things get very different when you consider the full nonlinear effects of gravity. So up to the 80s, what we knew about memory was only this. We only know about the linear memory. But later in the 90s, Lancheng and Christodoulou did derive a nonlinear contribution to the memory effect using the full nonlinear structure of the Einstein field equations. And I'm not going to talk about here, mainly because that is way more difficult. I didn't really get to it yet. But there also is nonlinear memory effects, which will play a role, for example, in black hole mergers. And it is important to notice an interpretation for this nonlinear memory. The origin of this nonlinear memory was given by Thorne in the 90s. And his idea and his calculations show that the linear effect is actually the linear effect due to the gravitational waves emitted by the sources. So if you have a black hole merger, for example, the way you get nonlinear memory is that you have the two initial black holes, and at the end, you're going to have the final black hole, where you're also going to have many gravitational waves that you emitted. And considering this gravitational wave that were emitted together, you can get the linear effect, and this will give you the expressions that you would find if you started with the black hole and computed the nonlinear effect. And now a brief message from our sponsor, which is the reason why I got interested in memory in the first place. I don't usually walk gravitational waves, so I find it a bit out of character for me to be interested. In fact, it is extremely related to gravitational waves. It is pure gravitational wave calculations. So why exactly am I interested in this sort of things? And the answer comes from very different areas in gravity and in quantum theory. So the first thing I want to talk about is about a very different fact, a very different calculation that was considered by Weinberg in the 60s in the context of quantum theory. So the setup for this calculation is you're going to have sort of scattering process. So the idea of, I'm going to use a bit of final diagrams, but I don't really illustrative, I don't really need to compute anything. But the idea of this diagram, for example, for those of you who are not familiar with quantum theory, is that you have some initial state in here, which I'm labeling as alpha, and you have this initial particles in there, so I'm throwing, I don't know, an electron, a positron, neutron, whatever I want. They interact somehow in the middle, and eventually a final state comes out. So this is just a scattering diagram. It's just depicting a scattering process. And the initial state is alpha, the final state is beta, and that's zero is the S matrix for this scatter. I'm considering in this diagram all possible interactions that we get. So everything that can happen in the middle of the initial and final states happens when we consider we're summing over all of those possibilities. So the calculation that Weinberg considered first, I'm not sure if this calculation was initially considered by Weinberg, but in the gravitational case, I do think it was. But in the electromagnetic case, I think it was preceded by some other researchers. And the idea we get is the following. Well, let's correct this scattering amplitude by doing the following. I'm going to consider that in this original amplitude, I'm considering only the exchanges of photons or gravitons, the calculation works with both, that are hard. By hard, it means that they have momentum above a certain cutoff that we're calling big lambda. So the photons that are exchanged in the middle in this diagram, photons and gravitons equal to both. They have at least this momentum big lambda. So they are quite energetic in the sense that they are above big lambda. But we also want to consider, if we want to consider the total amplitude, we need to sum also over internal lines that have soft photons. And by a soft photon, I mean a photon with momentum below big lambda. So lambda here is a cutoff that I'm introducing just to say what I consider a photon which is energetic and what is a photon or graviton that I consider not really that much energetic. So the terminology we usually use for this is hard and soft. So it is a separation between hard and soft photons and gravitons. So to consider the true amplitude, you're going to start with the amplitude that already includes all possible exchanges of hard particles or hard photons and gravitons. And then I'm going to add also the amplitudes that involve exchanges of soft particles. So this diagram represents the same scattering, but it also includes one exchange of a soft photon or soft graviton in the middle. And then you consider all possible diagrams which have one exchange. Then you consider all possible diagrams that have two exchanges. Then you consider all possible diagrams that have three exchanges, and so on. And you want to sum over all these things and see what exactly you get at the end. And to actually see what the result is.
It doesn't happen for photons. No?
Sorry?
Okay, no, sorry. The solid line are massive particle or photon or photons?
The solid lines, they can be hard photons.
Okay.
So they can be
in
photons.
that case, they have to be graviton, no? Because otherwise they wouldn't self-interact.
Yeah, they can be, but they don't need to be.
No, they do. I mean, they need to be, I mean, non-abelian photons. I mean, non-abelian needs to be.
No, I'm working with electrodynamics. So the solid line can be an electron, for example, or it can be an electron, can be a positron, can be a
Okay, like massive particle then.
Yeah, it can also be a massless particle, but if this is a photon, then surely you're not going to have this vertex, so you don't sum over this case. But this external lines need to be hard particles, so they are energetic in the sense they are above this cutoff lambda, so they can be either massive or massless or high energy. So for example, yeah, I draw all lines here, but let me ignore this drawing, and this here could be a photon, for example. and in the gravitational case, all of them could be gravitons and exchange gravitons on it. So, make sense? Sure. So we want to compute this amplitude, and due to the form of the result we'll get at the end, it's convenient to introduce another cutoff, small lambda, which is meant just for us to see how the result behaves for very small momenta. So I'm going to assume that all of these photons have momenta, or photons or gravitons have momenta above small lambda. And in the end, I want to take small lambda to 0. So small lambda is not really a physical parameter. I'm introducing it only as a cutoff, only so I can regulate my expressions and see how they behave as I take lambda to 0. And using these things, Weinberg managed to show you can actually find very simple relations between these different diagrams. So if you know the expression for this diagram, you can find this expression quite easily. It's just a factor times the original diagram. I'm going to show this later. And summing all of this for this case, what Weinberg found was this expression here. So the full amplitude, this considers all the exchanges of soft particles, or soft photons, or soft gravitons. This is not proposed in an amplitude, sorry. Is equal to the original amplitude, which did not consider soft particles, times this factor of small lambda over big lambda to the power of b, which is a positive number. This is a positive constant that appears in the calculation. And as you can see, when you take small lambda to 0, which is the physical limit we're interested in, we find that the amplitude vanishes. Why is this interesting? Why is this important? This is called an increment divergence. And what is happening here is that this prediction is telling us that when we consider an exact amplitude in quantum theory, in any theory that includes gravity or electrodynamics, and we consider all of these exchanges of soft photons, which we need to consider in the exact calculation, then the amplitude of the probability is going to vanish exactly. So the issue we have here is that apparently this calculation is telling us that all transition probabilities vanish in any theory that includes electrodynamics or gravity. So for example, in the standard model, this is saying that all amplitudes vanish, all probabilities vanish. I'm not sure if the amplitude should probability. And there seems to be a paradox because we do see scattering happen. In particular, this doesn't really need to be scattering. The calculation principle could be just for particle propagating freely, and you will still have this sort of issues. So it seems nothing propagates, nothing happens, and you have a paradox. So how exactly do you resolve this? Well, Weinberg noticed, and I believe some people might have noticed before in quantum electrodynamics, what they noticed was in gravity, is that you should consider the following. You're going to consider an original amplitude. So here I'm considering the full amplitude, which includes all of those soft particles exchange. This is why I changed the notation in the big ball from dashed to the field. So we're going to consider all of those diagrams, which are represented here. And what you need to do now is to also consider the emission of soft particles. So what is happening here? I'm assuming this time that my final state is not really beta. So there is a chance that when I'm walking in the LHC or my detector or whatever, I'm always going to know what I'm throwing in. So I can choose to throw in 2 protons or 2 neutrons or an electron deposit or whatever. But I don't really know what goes out. And there is the chance that I'm going to miss some particles that are not energetic enough. So for example, a very soft photon, a photon with very small energy, could not be detected by my detector. And I have, in fact, to account for the fact that the amplitude I'm actually calculating is not really this amplitude. This is not the amplitude I'm interested in. I'm interested in this full amplitude, which also accounts for the particles I'm missing. And here, what we are considering in this setup now is that the individual frequencies of each photon are still larger than or equal to small lambda, which is again just the cutoff, just so we can regulate the expression and see what happens when we take lambda to be small. And the total energy of all photons or gravitons is smaller than some constant E that I showed before. So this is just me assuming that the maximum energy in my experiment is E. And when we consider this setup, you can also make these calculations quite easily, sum into all contributions. What Weinberg finds this time is that this new probability, which includes this as emissions, is equal to the original probability in the sense of this diagram here, which also includes the exchanges of internal self-photons, times a constant times e over small n to the power of b, which again is a positive constant. And if you're not careful with this expression, or if you're not consider the behavior in here, you see that this is going to diverge. So you have another sort of divergence, but we already know the expression of this in terms of the original amplitude, which did not include the exchanges of self-photons. So considering that expression, so if I take this expression and throw it in this expression, I'm going to find now is that this full probability, which includes the exchanges of soft particles and the emission of soft particles, is going to be the original probability times constant times e over big lambda. Now, big lambda is a cutoff that I just used to say what exactly is a soft photon, and e is just another cutoff that I used to say how much energy I'm missing. So these things here don't really go to zero. I keep them finite. And in this case, you see that the final amplitude gets finite. So if you get something that actually makes sense. This is called, to the terminology, inclusive. They usually call inclusive cross sections. This is not yet a cross section, but you can get a cross section like this. And this is the main result from the Weinberg's 60 paper. What exactly is interesting about it, and what does it have to do with memory? So why the hell am I talking about this in a memory at time? And the thing is the way these calculations are performed. So in the original Weinberg paper, you have this small paragraph in here, in which it states how you compute those all those diagrams to like, how do you relate one diagram to the other so you can manage the calculations. And the thing is, when you pick some diagrams and fix diagram in your theory, and you add one soft graviton, in this case, it has to be a graviton, so this for hooks, it have a different but similar for photons. But in the case of graviton, if you pick your diagram and add one graviton line to one of the external lines of the diagram, what you're going to get is the same expression for the original diagram times this new expression here. Why exactly is this? This PU that happens in the end is summing over the particles. Eta is counting whether the particle is entering or leaving the diagram. This PU comes from the vertex that it just added. While this here is the propagator. You can draw the black. Okay. Let me stop share. So you're going to have some diagram like this here. Then I want to add a soft graviton line to this picture. So what I do here now is that I take the diagram and I choose, for example, this line, and I'm going to add my graviton line. What happens now is that I have this new vertex, so I have to add that PU term, which is the vertex interaction for the graviton with the matter, and I have this new propagator in here, which is a propagator for the hard particle that is coming out of the diagram. And when we consider all these things, we're going to have this propagator in here, we're going to have this vertex in here, so you get the product of these two things, and you take this and multiply by the diagram. That's what you're going to find is precisely in the soft graviton limit. So for a soft graviton, so we take Q to be very small, then we get this expression here, and it multiplies the diagram. If you're considering an external graviton, you later need to add also a polarization. If you consider an internal graviton, you also need to consider for the other vertex you add here. But the expression before you choose where the graviton lands is going to be this. And this result is known as Weinberg's soft graviton theorem. And this is the relation between an S matrix amplitude without the soft graviton and the S matrix amplitude with the extra soft graviton. So what does this have to do about it? The answer comes from the Brzezinski control paper in the form of this excerpt. What really matters here is this expression. This is the original Brzezinski solvent formula. I wrote it in a very different way earlier. But the result it has is this, that the change, the gravitational field, is going to be the change in this component here, which is the the quadruple chain formula I wrote earlier, but in a very different notation. And you again have here two momenta in the numerator, and in the denominator, you have this contraction of the momentum with this new vector k, and k is a new vector, which points backwards in time, and spatially it points from the source to the detection point. So you have this expression. And then the interesting thing that relates these two things is that this formula and this formula are actually the same formula, although they are derived in very different contexts. Weinberg was scattering elementary particles in a quantum field theory, while Rogensky and Todd was scattering black holes or stars in classical general relativity. And yeah, you can see by taking a look at this that the formula still looks similar. So you have two momenta here, then you have this new vector times the momentum. And here too, you have two momenta here in the numerator, then you have the momentum times the new vector. So they do seem alike a little bit. And who, to my knowledge, noticed this relation between the two expressions were Schrödinger and Zhigwedov in 2016. And you notice that the Rogensky-Todd formula is actually exactly the Weinberg subfactor up to a Fourier transform and a change of notation.
No, I understand the PQ from the propagator in the Weinberg's formula, but where does the PQ comes in the Rogensky-Todd, the cap of the K beta, where does it come from?
Yeah, what you're gonna do, I find it much easier to derive this formula, but you can guess this thing here to look like a momentum. That is not really difficult. We're gonna have the mass in the denominator. And then I think the trick is that you write the mass in the denominator as product of the two vectors.
The mass.
Yeah, I'm gonna make here.
Okay. And then the mass denominator. No, but that would then should be a four momentum product. I thought there was a three momentum product, wasn't it?
No, it's a four momentum.
Four momentum.
Yeah, the Rogensky formula is a little bit weird. It's just a notation they use. They do use this notation with boldface for the formula.
So E is the momentum of the source, and K is the momentum of the gravity.
Yeah, K you can interpret as the momentum of graviton, but in the original paper, they're not thinking about gravitons.
The gravitational wave.
Yeah, it's a gravitational wave. But they say, I think it's written here somewhere. K is the path direction new form vector from observer to source. So yeah, I guess it is the momentum of the wave. Well, up to just on. It is path directed rather than diffusion vector.
Okay.
So we have this relation between the two formulae. They're actually the same formula up to a Fourier transform. And another point that Schrödinger and Zhigwedov were interested in is that when there is a symmetry behind Weinberg software theorem, the reason to think of this is because the Weinberg theorem is a relation between different S matrix elements. Typically, when I have something like this, we have that there's relations fixed into an S matrix element in terms of others. There is a hidden symmetry behind it. And they're interested in knowing whether what is the symmetry in the case of gravitons. And you actually do have a symmetry. It's called the Bondi-Master-Sachs symmetry, the Bondi-Master-Sachs transformations. And the basic idea of them is the following. If you have a asymptotically flat space-time, so of course, Minkowski, which is the easiest example, when you go to infinity, the group of symmetries in infinity is not only the Poincare group, but actually it is the Poincare group plus infinitely other symmetries. So the basic idea here is that if you are inside Minkowski space, so if you are at a finite distance from the origin, the symmetry group is going to be the Poincare group. This is usual spectral relativity, nothing really special about. But when you go to infinity, you still have the Poincare symmetry, so the Poincare symmetry hold every place Minkowski. So when you take the limits to infinity, they still hold. But many other symmetries also occur. And this was a surprise when Bondi-Master-Sachs found it out in the 60s, because no one had done this calculation before, and everyone was expecting that the calculation would be just a Poincare group, and that's it, and that's not special, but that's what everyone expected. But it did found that there were definitely other symmetries that nowadays we call super translations. The reason is because they are similar to translations. Let me. Yeah. Which is the following. You usually there's diagrams. So this is a depiction of Nickolas space-time. There's lines here represent infinity, and side here we have finite regions of Nickolas space-time. So here we that is outside the real infinity, and the super translation is that at each point in infinity, you're going to translate time by a different amount depending on the direction that you're looking at. So this is a more complicated notion about translation. When you have a time translation, you just translate all of these guys equally. When you have spatial translations, it is a bit more difficult when you do the calculation, but it's still quite simple. The dependence on the direction is with an L equals 1 spherical harmonic. So that's usually cosine, sines, and an exponential, something like that. Super translations can be much more complicated. They involve spherical harmonics with higher. But the main picture is this, that you translate time at infinity a different amount depending on the direction you're looking at. And these are the symmetries that Onimax and Sachs found at infinity. And what is interesting about this related to the memory effect is that the Weinberg software computer actually follows from EMS invariance. To my knowledge, it was originally by Stronger and collaborators, and the two references here, 2014, 2015. And what you do is to be a bit more technical, the Weinberg software computer is a word identity for the BMS invariance, which is just a quantum theoretic way of saying that BMS invariance implies the software computer. They are related deeply in the sense. And also the memory effect can be understood as a physical realization of a super translation. So the reason from a more theoretical point of view, you actually have the memory effect when you propagate away to detectors is exactly because what is happening is a super translation. So you can understand the passage of the gravitational wave as a physical realization of a super translation. And what I found interesting about this is because this means that the memory effect is a way to pick very special symmetries of gravity that are only at infinity, and hence difficult to consider in usual situations. But memory is a passage to that, and also to all of this beautiful infrared structure that you have gravity, which also includes the software of the theorem and so on, which are very deep statements of how gravity works. Are very fundamental for effects. For example, the soft theorem is called the soft gravity theorem, and the analogous soft closure theorem, which is real similar, just changes the vertex a little bit. So instead of having two momenta in the very high moment one, because that's how photons interact, you get the soft closure theorem, and it's essential for you to actually understand how amplitude work in quantum theory. And Stronger denotes this by using this triangle, which follows the infrared triangle and his lectures on the structure of gravity and H theory, in which you have these relations between a memory effect, H soft theorem, and A asymptotic symmetry, saying A rather than the, because after this was discovered for gravity at many different times. So here you have this two lags in the 60s, this lag in the 70s, and you find the relation between all of them only in the 2010s. And after you have this triangle for gravity, you cannot actually see it echoing in other theories or orders in perturbation theory. But for example, you also have analogous triangle for quantum electrodynamics, in which you have an electromagnetic memory effect, which is very different in the case of electrodynamics. You don't really have a change, a shift in the permanent, a permanent shift in the separation between two detectors, but actually we have a changing phase of an electron, something like this. So this is a reason for why we didn't notice the memory effect in quantum electrodynamics until the 2010s, because it's way more quantum in nature than the memory effect in general relativity. The soft theory for quantum electrodynamics is also Weinberg's, And the asymptotic symmetry is called large gauge symmetry, which is a gauge symmetry in electrodynamics that doesn't die off at infinity. So it stays finite at infinity, and it is large in this sense. And you actually have other triangles for other situations. You have other triangles for gravity. For example, when you consider the subleading subfield, so considering the leading term in 1 over the frequency of the field, and you consider 1 over the square, you get a different subfield, which is due to the distributed dual. You have different asymptotic symmetries, which are called super rotations, which are way more complicated than super translations. And you have what is known as the spin memory effect. And also another thing that I find really interesting about this is that memory super translation can shed light on black hole operation. So in a series of papers, the last papers of Stephen Hawking, Hawking and Strominger argue how you can use these ideas of super translation and hence with memory to better understand information loss in black holes. Namely, since you have BMS invariants, you also have infinitely many conserved charges associated with super translations, and these charges must be conserved in black hole evaporation, which leads to more information being preserved in black hole evaporation than we previously thought. And although this is not so information paradox, there is a paradox to the end of. But although it doesn't shed all of the light with light into this puzzle, it sheds some light. And finally, a few comments on measuring memory. I'm going to be quite short in this because I know nearly nothing about measuring gravitational lengths. So just going to make very brief comments. First, there is what I mentioned earlier, that binary modules of linear memory vanishes. The reason is because the system is bound, so you have to consider the two initial black holes as being one single body, and at the end you have one single body. So the change in the quadruple, the derivative of the quadruple ends up vanishing. So you don't really have linear memory in those cases, but you do have nonlinear memory, which is, as I mentioned, due to the emission of gravitational waves during the merger, which then you can consider as extra outgoing bodies, and that generates more gravitational waves than you can actually talk about. Some references on measuring memory are just once here. I also saw a paper earlier today on the archive about measuring moderate laser, but I won't show the abstract here too much. In the case of LIGO, it is difficult to detect memory, LIGO, Virgo, etc. The current detectors. It's difficult to detect memory because nonlinear memory takes time to build. So it's not really a fast phenomenon. And as far as I know, LIGO is only sensitive to larger frequencies, not really to the small frequencies of the memory effect. I've heard though that there are people there are books on trying to measure memory by stacking together many different events and detecting memory by them. And I yes.
What do you mean the detectors are not inertial?
In the sense that they are stick to the other.
Yeah.
They're stuck to the other. They're not falling, free-falling.
Yeah, but I mean, well, no, but that's true, no, because I mean, on the time scale of the observation, they are. Otherwise, you wouldn't see gravitational waves. Now, what you see is the displacement of the mirror, and the mirror are freely falling. Of course, not in the Z direction, but in the XY direction, they are freely falling. Otherwise, you wouldn't see them.
That makes sense. I'm not really sure. I don't remember if I
So for sure, they're not freely falling in the Z direction, but they must be. Otherwise, they wouldn't react to gravitational waves.
No, that makes sense. I may have missed something. So I think that either maybe the time scale for memory to build up, they can be considered inertial. Not sure, I'm guessing. Or I got it wrong. I'm not really sure. I can try to like.
No, the problem is the noise, because then the memory effect, because it's important, the small frequencies. And basically, you see an offset between the beginning of the gravitational wave and the end of the gravitational wave.
Yes.
And that goes well below the Earth. And the problem of the noise that makes the detector blind to everything that happens below 10 Hertz.
Mm-hmm.
But then, as you said, if you stack many observations, the noise is not coherent and deep into the observation, so it doesn't add up coherently. Whereas the signal, if it's there, it does add up coherently, so you can both to see by stacking.
Mm-hmm.
No, but I think that's still with the, yeah,
So
I don't know.
it's roughly 2000. So it's expected to see during observation of 5.
And this is always the same place. As you said in the beginning, as it could be either closer or further away. So if it's cancelled out, then stacking will not see.
Yeah, it depends a bit on the specific situation. Yeah,
It's like the supernova, the light curve is the same once you scale by the parameters. Now, like here, the effect is the same after you rescale by the parameter. The parameter you measure from the gravitational wave, you rescale it to give the same shape, and then you stack it. So, of course, it depends on the stress per parameter, the exact shape, but those you measure.
To visit the class, the waveform will be stretched.
No, the waveform is this, the zero, the waveform is displaced. So you have some oscillation around some zero during the inspire, and then the readout oscillates to a slightly different offset. The height of this offset is exactly the memory effect. Okay, this is huge exaggeration.
yeah, actually,
That it would be always like a delta in the same direction, not be like sometimes below, sometimes above.
I think that may depend on the specifics of the source of gravitational waves.
But the point, but that doesn't matter because, as I said, once you measure the physical parameter, that's the physical parameter of the binary, you know how the effect is. So you can rescale it by this parameter and to add it coherently. I mean, quantitatively it will be different from event to event, but you know how to rescale it because you know general relativity density.
It is expected to, or easier to measure memory in individual events because it responds better to low frequencies. And this is exactly natural in the sense that it is really revolved. Inertia isn't really essential here. So I've also seen people arguing that the Cosmic Explorer and the Ocean Telescope will be able to measure memory in individual events. The most important thing here is really responding better to low frequencies, since memory has to build up longer time scales. So I decided to make some further reading for the slides. The main reference I followed to learn the basic linear and linear memory effects is this Euros by Viedi Konrad. Viedi is a mathematical relativist who works mainly with memory, as far as I know. She was a student of Christodoulou, who discovered linear memory. And Konrad was one of the authors of the original paper that discovered linear memory. This is a very recent paper that reveals both the gravitational wave displacement memory effect, which is the one I discussed. And you also have a velocity memory effect, which is a little bit different. And you have a final velocity difference between the two factors. So one of them is shifting away or towards the other at the end of the process. But the astrophysical setups for you to get this sort of memory are different from scattering, which was what I was the most interested in. There's things about subfields and asymptotic symmetries. There is this nice book by Schrödinger, who worked a lot with this quantum methods of memory and with the symmetry of neural activity. It's called actually the structure of gravity engaged theory. It's based on a course that usually gives in Harvard on this very same topic. And about the infrared divergence in the subfields, there's the quantum theory book by Weinberg, the first volume, which discusses the infrared effects. In the particular case of quantum theory, so the soft gravity theorem and the infrared divergences that I consider by explaining that subgroup. So I have a list of references here. I can give to you later if you're interested. And finally, I want to make some mention, which is on the school I'm organizing along with some collaborators who has been helping us a lot with getting this done. And it's going to be a fully online school, no registration fees. It's called GRASP, the first symbol of gravitational physics. You have this website here where registrations are open as of now. And we're going to have mini courses in black hole perturbation theory, the physics of the early universe, gravitational lenses, infrared symmetry of general relativity. This is me, philosophy of relativity. In infrared symmetries, I'm going to talk more about the EMS symmetries that I mentioned earlier. Given all of the necessary machinery, advanced general relativity to understand the DMS errors and DMS symmetries. And eventually, I want to also mention a bit about how this relates again to memory effects to software theory and all the ideas. And quantity theory. So that's, thank you very much for your attention, and I'm open for any questions.
During the lectures for this.
Black hole propagation theory is Victor Guimarães. He's a master's student at UFABC. The physics of the early universe is Fazla Sugar. She's a student at the Instituto de Ciencias Nucleares at the Universidad Nacional Autónoma de Mexico. She's a student of the university. Gravitational lens and Coreani. He's a PhD student at the Jet Propulsion Laboratory in NASA. And he's a former student of Eduardo Sapir. As well, relativity, and following the relativity is Antonio Ferreira, who is currently a postdoc at Utrecht University in the Netherlands.
This memory effect is the fact that after the passage of the Gaussian waves, objects will have a different distance. So will stay separated by larger.
Yes, the distance shifts permanently after the passage of the gravitational. It's this. So to have the two detectors at first, so it's the two inertial objects. They need to be a large R so they can neglect the 1 over R squared direction zero to the Riemann tensor. And then a gravitational wave passes through them, and they are permanently shifted. So they got more distance or less distance permanently after the passage of the gravitational. So you can interpret this graph as either the gravitational wave itself, but you can also think about it as the initial separation between as the separation is much more time of the two. So they oscillate for a while as the gravitational wave passes. Eventually, the gravitational wave has passed by, and they are permanently shifted.
But it's called memory, so technologically it appears in the same way, but the fundamental theory origin is different from the non-linear and the linear. Okay, so this is the linear, that is an outcome of the non-linear, but phenomenologically it's very similar. It's very the same. Yeah.
And it's realistic, for instance, to measure it in macroscopic objects, for instance, the distance between the Earth and the Moon, will it change after the passage of Gaussian waves?
It's not an oscillation, that's the point. It's not an oscillation. It's a displacement. It's almost zero frequency. It's not an oscillation.
But if you measure the distance between the Earth and the Moon before and after the passage,
Yes, but what is the effect after?
Yeah, that is really tight.
It's on the order, the same order of the amount of the gravitational wave that we do measure like the kilohertz. But one thing is to measure something that is sustained 100 times per second. One thing is to measure something that is called the perturbation of the gravitational field of the Earth is 10⁻⁸. And this effect is 10⁻20. You never measure 12 order of magnitude speed of. But why can you measure 10⁻20 at the kilohertz? Because there is nothing else at the kilohertz. Okay. So you don't measure an offset of the static gravitational field. So you have plenty of gravitational fields well above that around us. If even a planet at the other side of the galaxy has a Victoria potential higher than that.
Didn't read much about the Irish telescope, but the main point I saw bring more or less sensitivity to low frequencies, so you can actually see the view.
Okay. There we thank Nickolas again. Yeah, I mean, it's ahead, but I don't mind starting at right now. Sorry. Yes. Well, the law, we can do it while we set up. And I'm using my laptop. Yes. Yes.
Daniel. Vai. Você pode colocar no autor dele?
Pode sim.
Fechado. Tá cheio, não. Então vai fechando também.
Que não tem previsão.
Venezuela. É outro evento?
Não, não pode.
Tá, sapato, deixado,